Welcome. My name is Alex Wren, and I'm here today to give my analysis of the first lecture in a series of lectures by Professor James Elias. James is an acquaintance of mine, and we're starting to. He wanted to get some of my feedback on these courses he's been constructing, so that is what I aim to do here today. So let's get going. The title of the course is An Inductive Summary of Physics. And again, like I said, the instructor is Professor James Elias. And what my goal here today to do is I want to sort of give my best summary of what I think James is trying to say, and then give some spots where I think it's particularly memorable, and some questions that I have. Now, I'll be doing all of that both in sort of the general approach that he's going to take, which he covers in this lecture, as well as sort of the specific examples that he comes up with, or that he covers today. So the specific investigations that he looks at this time, they're largely early astronomical phenomenon discovered mostly by the ancient Greeks, but some of them by cultures that even predate that. So let's before we jump into that, though, I'll start trying to summarize what I think the basic approach and premise of this course is. Okay, so the idea here is that discoveries in physics are going to be presented in a roughly historical order, such that we're able to come to the conclusions inductively. Okay, yeah, I just read from the slide. Oops. Now let me try and sort of sum up what I think that means. The idea here is that if you present scientific discoveries in the same order in which that they were discovered, or similar order in which they were discovered, you go through a lot of the thinking that the discoverers had to go through. And in so doing, it helps you sort of understand not just that they came to a conclusion, but why they came to a conclusion. So what evidence did they have for it? What reasoning did they use for it? So that is my sense of the goal right here. Now, the idea from the instructor's mouth is that he wants to make sure all the conclusions he presents are proven. And this is contrasted with the idea that you can't just say a scientific conclusion. The professor can't just say a scientific conclusion and consider it proven. So in this case, James wants to present the observations, the analysis, the thinking, the integration that was required in order to come to certain conclusions. I'll get into a bit more into that in a bit, but that's the general idea. So the general approach, the general idea here is that we're going to try to start from more or less a blank slate of scientific knowledge claims. So we all have a bunch of scientific knowledge claims floating around in our head. The idea is to pretend we don't know any of those. And we're going to go back to the very beginning when we don't have anything but our observations and try to build up a body of scientific, particularly knowledge about physics, from there. Okay? Now, the general method that is going to be used in here is what Professor Elias calls the Mqic Method. And basically, these are the four different categories that he's going to present in terms of each sort of investigation that he goes through. Now, one of the steps, I, actually stands for investigation. But the M stands for motivation. So first, he'll want to give an idea of why this line of inquiry was interesting. In particular, he brings up how it is beneficial to the human condition, or how this new knowledge, this pursuit of this new knowledge could benefit the human condition. So that's largely the idea behind the motivation. Q is what question did that motivation motivate? So there was a motivation, and then what specific question was ultimately asked as a result of the motivation? I stands for investigation, tends to be the main focus of science classes. You're largely taught about the investigations, or what the investigations uncovered, so on and so forth. And finally, C is the conclusion. So that is succinctly stating a the conclusion that was reached as a result of the investigation. So succinctly stating it in a new syllogistic form, if you will, that the idea that was come to as a result of this investigation. Okay, so that is my my take on what I think the general approach is, what I think the professor's trying to accomplish here. So I had some general questions on this. And the first is the criteria. What are the criteria going to be for inductive evidence? Now, I want to flesh this out a little bit, but the main problem with either a historical or an inductive or anything like that approach is that there's no possible way to present everything. You have to be selective. So that's always part of the problem, and that's fair. That's a big part of what education is. It's about being selective and choosing what you're going to present. But when you're looking at a historical process or an inductive process, I can see a tension arising when it comes to, okay, how deeply am I going to go into the necessary understanding of different aspects of the induction? So this is something that I saw come up in this lecture that I do have questions about. Particularly when you're presenting the observations, when you're taking this approach and you try to present the observations, is it enough to say this person observed this phenomenon, or is it better to actually show the phenomenon? And if it's better to actually show the phenomenon and let the students or learners, try to induce it for themselves, how deeply do you go? How much time do you really spend on that? Because, like I said, you do need to be selective. So I do think that's going to be a balancing act, and I do think that that it's going to raise some interesting questions about what's appropriate for both for teaching and for discovery. If you're trying to use this as just as an inductive, run through the existing scientific knowledge that we have. Okay, so that's kind of the idea there. All right. Now, another question I have is there is a certain sense in which I do think the historical approach limits you a bit. And what I mean by this is not only do you not have access to the advanced scientific conclusions, I think that's actually kind of the point, but you also, in not having access to those scientific conclusions, you're also limiting your access to you're limiting your ability to observe certain things. So the main example I came up with here is that when thinking about something like, say, the sun path, this is brought up in this lecture, and the sun path having the circular path. Well, this was largely inferred from the ancients were largely able to infer this, and they inferred the circular path of the sun correctly. My question then would be, okay, well, if we're going to limit the historical if we're going to limit ourselves to the historical narrative, do we stop there, or can we take observations that we could make today that would be relevant there? So in this case, the relevant example would be to go north of the Arctic Circle during the summer months, where you could see during the course of the day, the sun is it's moving in a circle. It never sets, it never rises, it just sort of circles around where Polaris would be is basically what it's doing. So the ancients wouldn't have made that because they would not have been able to make the trek to the to north of the Arctic Circle. So the question then is, okay, well, is this a valid observation to present in this approach or not? So that's another thing that I found it interesting to think about. Another question I had is this idea of going back and starting from a blank slate. So sort of trying to doing your best to forget all of the previous knowledge claims that have been made. Is that going to be required for this method? And if so, why? So the basic idea here that I have is that people have a large mixture of knowledge claims floating around in their head. Is the basic prescription here going to be, okay, you need to ignore all of that until you can prove it inductively? Or is there some sort of approach where a person can examine an individual claim and say, well, how do I know that that's true? So that's kind of the idea. What is the general approach for how a learner who's taking this class should deal with their previous knowledge claims? Is the general advice to say, okay, ignore all of it until you can prove it all, or is the general advice different than that? So that's another question I have. Now, this is possibly considered a nitpick, but it is a question. Early in the lecture, Professor Elias has some commentary on both faith and philosophy. The commentary on philosophy largely goes into the view that the formal practice of science rests on certain philosophical principles, and Professor Elias brings up what he thinks those principles are and the philosophers he thinks are responsible for them. I don't really understand the purpose of this in this context. There's no contrast with other approaches, what other philosophers have thought about this approach, and that doesn't seem to be what this class is really about. It's not really about the philosophical approach to science. It's about doing science using a certain approach. So bringing up the commentary on philosophy, I don't know if that's relevant to the overall content of the course, but it seems a little superfluous, at least in this lecture. There's also a comment that the professor makes on faith that I did not understand the purpose of that either. So the specific comment I'm referring to is that saying you're going to take something on faith is the same as you're going to take something on someone's say-so. Perhaps that's true. Now, that is certainly not accepted by people who take faith seriously. Now, at the end of the day, that statement, faith is identical to taking something on someone's say-so, is nothing more than you saying so. You haven't proven that. So, if that's going to be a focus of the course, if the focus of the course is going to be, well, I'm going to prove that, faith is equivalent to just say so, then that's one thing. That's one thing it's a valid line of inquiry. That does not seem to be the purpose of the course. And furthermore, it seems unsubstantiated when given the way it is. I don't see that doing anything but alienating people who think about their faith differently. That's not how they think about their faith. They don't think of it as, well, I'm just taking someone's say-so for something. They have certain experiences that they take very seriously. So I don't understand the purpose of doing that as well. The next question I have is, what does it really mean to have a motivated question? Now, this is described a bit in the course of the lecture, but the main thing that I remember is a comment that a professor made about how if scientific research has no possibility of improving the human condition, then it is a waste of time. Now, again, that may be true. However, it's a little unclear to me how people know in advance whether or not their research is going to be able to improve the human condition before they do it. So is a claim that there's no possible way that this can improve the human condition, does that need to be proven? Or if a researcher can't present compelling evidence for how the answer to this question would improve the human condition, is that sufficient reason for them or for their research to be judged a waste of time? So when it comes to motivation, I'm a little unclear how specific the motivation needs to be. Now, I'll touch on this when I get into the specific investigations, but a lot of times it seems to boil down to the idea that people were curious about something. Now, is that a valid motivation? Is the satisfaction of curiosity, is that a sufficient improvement of the human condition to do research? If yes, then it seems like that's something you can always tack onto the motivation. If not, then it seems like then you're going to limit a lot of the potential inquiries that you can make. And I think many of these inquiries under that rule, that curiosity is not a valid pursuit, would have been ruled off limits if we were going to take that prescription seriously. So that's and like I say, I'll discuss this a bit in some of the motivations of the different investigations here. Okay, so next, the investigation phase, it seems a little bit condensed for me. It seems like there are multiple steps involved in the investigation phase that are all kind of lumped into one. So kind of let me tell you what I mean. And I think this is particularly important since I think a big chunk of what this class is trying to do is describe the investigation phase. So I do think the investigation phase could be parsed a little bit more. So I think you could parse that into, say, the establishment of context. What was the existing context when this investigation began? What were the observations that were made? That's another thing. What were the integrations and connections between those observations and the existing context of knowledge? And I think those are three sort of different things that need to happen. Maybe not. Maybe all of them don't need to happen. Maybe sometimes there are no new observations to be made. It's all just about making connections. That could very well be. But I think having a little bit more detail about what goes on in the investigation would be very useful. Then lastly, I wanted to talk about in the conclusion, particularly if going back to my motivation, if curiosity is indeed a valid motivation, a lot of times these conclusions then point to new questions. I think it would be a really interesting and really good idea to talk about the questions that come up as a result of these conclusions. Now, that does happen a bit in this first lecture. I'll try to point that out. I think I've got that in the notes for this commentary, but I do think having that be sort of a more explicit part of the conclusion would be valuable. So with that, I'm going to move on to the next to the first investigation. Okay, so the first idea that we look at is the causes of the seasons. So first thing I'll do is give a summary of what I think the general progression of this idea is, and I'll do that using just kind of bullet points with the Mqic method. I'm going to roll the motivation and question into one because those often come very together. So the motivation and the question here is that basically there was no prior knowledge, no prior scientific knowledge to speak of. least not about astronomical phenomenon. And people wanted to know the cause of the seasons. So that motivated, the question, what causes the seasons? Now, the investigation basically boils down to someone drew a correlation between the temperature, the duration of daylight, and the angle of the sun in the sky. All three of those things change during the course of as the seasons change. And the ultimate conclusion was that the duration of the sunlight is the cause of the seasons. We found that the temperature lags the longest day by about 60 days. So the warmest day of the year comes about 60 days after the longest day of the year. So that wasn't all didn't all happen on the same day, but basically this was the conclusion we came to. So what I found memorable about this one is I liked the description of the observations. I thought that these were very relatable. That it was something that students could not only imagine doing themselves, it's something they could actually go do. Like, you could actually go find temperature data, duration of daylight data, and possibly angle of the sun data. That's probably a little bit harder to find, but I'm sure it's out there somewhere. So it's all something you could do. Plus the way, the description of the way particularly the angle of the sun was measured using shadows. Very interesting. A lot of people wouldn't think of it. I think it's a very good presentation of it. The questions I had about this idea. The first one comes in the motivation. I'm unclear about what the argument is about why this was a motivated question. So the impression I got was that it was being claimed that the knowledge context of the people asking this questions did not know the causes of the seasons, but they also didn't know that the seasons would change. Or maybe they knew that the seasons would change, but they also didn't know when. So basically the motivation of this question was to help them figure out the timing of the seasons. Now that doesn't seem quite right to me. Like, that doesn't jive with what I know of the history of science, but also just the history of civilization. I think that, people could time the seasons relatively accurately long before they knew what caused it, or long before anyone thought to ask the question of what caused it. Now, maybe I'm wrong about this, but one way or the other, I do think that is something you need to consider when talking about these motivations. Another question I had was in regards to the conclusion. I have always been under the impression that another aspect of why the angle of the sun affects the temperature is that there's a greater concentration of radiant energy striking the Earth, and that has to do with the fact that the sun is closer to being directly overhead. So if the sun was directly overhead, the radiant energy would be concentrated in the greatest or in the smallest amount of area once it strikes the Earth. If it's striking at an angle, you have the radiant energy striking a much broader patch of the Earth. So that was the idea. That wasn't brought up here, and I'm not entirely sure why. Maybe that was not something that would have been discovered here. Nevertheless, even if it isn't, I do think in this context it's worth mentioning, at least insofar as to say this investigation wasn't yet complete, and there is an additional component to understanding why a higher angled sun warms things up, warms the land up to a greater extent than a lower angled sun. All right. Next idea that we looked at was the phases of the moon. So again, start with the summary. The motivation in the question were basically knowledge of the moon phases might help early peoples make better decisions. So the question became, what causes the moon to change? The investigation was, well, the phase changes are fairly predictable. You know, we go from a new to a crescent to a quarter to a gibbous to a full, back to a gibbous, but gibbous is on the other side, to another quarter moon, 3/4 moon, to another crescent, back to a new moon. And furthermore, the phase of the moon is going to be very predictable by the relative location of the sun and the moon in the sky. So basically, the idea is that the closer the sun and the moon are to one another, the smaller the moon phase will be. So the closer it will be to new. And then when the sun and the moon are in the same approximate location, that is when you have a new moon. When they're on opposite sides of the sky, that's when you have a full moon. Now, the conclusion from this is that the angle between the sun, the viewer, which would be on Earth, and the moon determines the phase of the moon. So that was the ultimate idea, and the reason is because that viewer, the side of the moon that the viewer sees, is partially lit sometimes, and that's ultimately what causes the phases of the moon. Some memorable aspects about this. I did like the diagram relating the positions of the moon and the sun. I thought that was useful, particularly as a visual aid to sort of be able to picture what the observer from Earth would be seeing relative to what's actually happening for the illuminated moon. So I thought that was pretty good. I do think that could be extended, and you could show more examples of that, but whatever. Like I said, I thought that was good. Some questions I had about this one. All right. The main thing I have always wanted to know when I have taught this before, I have had real difficulty showing students who've never bothered to go look the relation between the location of the sun and the moon and the phase of the moon. It's difficult, one, to get both of the two in a picture, and two, to get the exposure right such that it makes sense. So I've not been real successful in being able to show that. I would just just be curious, is there a good way to show this in a video or an online medium, or is this the kind of thing where you say, you're going to have to go make observations of the moon and the sun for a month, which, is a fair assessment, or fair claim. Okay, so moving on to the third, the daily path of the sun. All right. So first of all, the motivation and the question. Understanding, just again boiling it down, it's more complicated than this in the lecture, but understanding the sun's path might teach us important things. So what exactly is the sun doing, in particular when we can't see it? It's kind of clear what it does when we can see it. It rises in the east, sets in the west, roughly. That changes a little bit. Sometimes it actually rises a little bit in the northeast. Sometimes it rises a little bit in the southeast, and does those kind of things. But what is it doing when we can't see it? Okay. And so that's what this investigation about. Now, the investigation roughly went like this. While it's visible, we can see that the sun moves at around 15 degrees per hour, and if we assume that's exactly what it's doing, such that its path makes a circle, then this will accurately predict the sunrises. So if we assume it proceeds, on that circular path, at the same rate while the sun isn't visible. So the conclusion then is that the sun travels in a circular path, and this circular path, changes a little bit with the seasons. So that was my understanding of that one. Now, one of my favorite things about this idea is I really like this snow globe representation of the celestial sphere, sort of where you present the Earth that an observer would be standing on sort of as a flat plane, and then the celestial objects as kind of on a dome over their head and then moving through different locations of that dome. I think it's a very good way to visualize celestial motion, particularly for people who haven't thought about it much before. So I think that's that's a good thing to do. Always found that particularly useful. The questions I had about this one. If you're going to start talking about the sun path, I do think that the motion of other celestial bodies I do think that logically precedes any, deep investigation about what the sun's doing. So it's not just the sun that's doing this. It's all the celestial bodies. All the celestial bodies cover roughly a similar daily path. Now, most of the time we can't see those when the sun's out. The sun and the moon are really the only celestial bodies we can see when the sun's out. But when the sun's not out, we see the stars, the planets, the moon. If it's out when the sun's not out, they're all going along the same type of path. Now, the reason I think this would be useful is because you could look at certain stars in the northern sky and just you could actually see a lot of those stars never set. So the stars of the Big Dipper, they never set. And you can actually verify that indeed they do go around in a circular path. Now you can't see them during the day, but you can see very clearly they're moving around in a circular path at night. And the idea is that you can then relate that to the path of the sun. So I think that is, the connection to other celestial bodies, a very important integration to make in this kind of, as you investigate this idea. Now, the other question I had, it wasn't entirely clear to me, but what is the nature of these different circular paths that the sun is traveling on during the changing of the seasons? I'm sorry. So when the image kind of showed two different circular paths, one during I think the equinox and then one during the solstice. Now the question I would have would be, okay, now like are those circular paths, are they parallel circles like latitude lines, or are they just tilted circles where they're all meeting at some central point like meridian lines? So it's not entirely clear to me what's going on there. And again, I do think looking at other celestial bodies would make that question more clear. It wasn't, let me just restate, it wasn't clear to me from the presentation what was going on there. Now, I've already talked about this a bit, but I also had a question about the limitations of the historical approach. So, for instance, we see this. Is under this approach, is it valid to then go make observations of the path of the sun at different locations in the earth, particularly locations that the ancients wouldn't be able to reach? So, could you go, north of the Arctic Circle and then do a time lapse where all you see is the sun going around in a circle during the summer months around what would be Polaris? You obviously can't see Polaris, but that's basically what would be going on there. Is that a valid approach or not? Does that not fit into the historical approach that's being used here? Okay, next one I wanted to jump into, next one that was covered was the cause of the lunar eclipse. So the motivation question, lunar eclipse is observed, and it's a different phenomenon. It's observed to be a different phenomenon than the lunar phases. So the idea here is, well, what causes this? What causes this sort of weird shading of the moon that's distinct from the lunar phases? Now, the investigation, as I understood it, is that we hypothesize that the Earth's shadow is falling on the moon based on the timing that it occurs. The only time we ever see lunar eclipses are when the moon is full. Now, what this means is that basically the sun and the moon have to be on opposite sides of the Earth. Now, we know that the sun is, anything light strikes casts a shadow, so the idea is, could it be that the shadow is the thing that's causing it? Now, the question arises, well, wouldn't we see one every time we have a full moon? And the idea is that only on closer investigation do we observe that these things need to be in perfect alignment in order to see the lunar eclipse. So we have to have complete opposition, not just, mostly in opposition. And there's a reason why we don't have complete opposition every lunar cycle. So the conclusion is that, yes, indeed, a lunar eclipse is caused by the Earth's shadow falling on the moon. So I do like the question. During the course of this investigation, the question comes up, like, if this hypothesis is true, why don't we see it more often? Like, I think that's it's a very logical thing to ask. It's something students might ask. It's probably something people who were positing the first explanations to this asked themselves. So I do think that's something to keep in mind. And that approach, like questions that come up during the course of the investigation, is a good thing to do, because a lot of times that happens. Some questions I had about how this was presented. Again, I have questions about the implications of the motivation statement. So what exactly is being said in the motivation statement? Now, as I understood the motivation statement, getting into the details a little bit more, the claim is that before people decided they wanted to investigate the cause, and Professor Elias points to the Greeks as the first ones who investigated the cause of the lunar eclipse, that this would just be sort of a random, ununderstood phenomenon that, possibly with mystical significance, possibly heralding war, whatever. I don't understand if that's the actual claim being made or if it's something different. If that's the actual claim being made, that does not jive with what I understand about the history of astronomy. So I know that the Babylonians were predicting eclipses millennia in advance of what was contemporary with them. So they predicted well into this millennia, the millennia we're currently in. They were able to predict the timing of eclipses, and that is because they understood the cyclical nature of them. Now, I don't know enough about it to say whether or not they understood the cause, but they certainly understood that this was a cyclical phenomenon, and that meant it was predictable. So I don't know that I buy the idea that this is just seen as some sort of random, scary phenomenon that nobody had any understanding of at all before people figured out the cause. Another thing, it seems to me that partial eclipses, particularly partial lunar eclipses, would be significantly more common than total lunar eclipses. Now, this means that, as presented in the motivation statement, somebody just eventually observes a total lunar eclipse and wonders what the heck is going on. But I feel like it would be I believe it would be much more likely that over the course of time, people would observe these partial eclipses where you had little patches of the moon going in and out, and people not really understanding why that was the case. So I think that the historical narrative presented here, it doesn't quite make sense to me with what I would imagine would be most likely to happen based on which phenomena are more common. Last thing, the phenomenon of the red moon is brought up during this investigation, but it's not ever explained. So I just from a teaching perspective, I have to ask: is that the best idea? Now, why does the moon turn red? Well, the understanding of that is somewhat complicated, and I don't know. I don't know, who first posited that, but if it's going to be brought up, it should probably be explained. Otherwise, I would imagine it would be better to let it lie and think about that as an investigation for another time. Okay, so next one was the shape of the Earth. So this was the fifth investigation. Basic summary. Knowing something about the shape of the Earth would be useful. So the question arises: well, what is the shape of the Earth? Is it a flat plane? Is it a disk? What is it? And the investigation was bringing together a bunch of different drawings of Eclipse to show that the shadow is always a circle, and there is only one shape of object that always casts a circular shadow, and that is a sphere. So the Earth is spherically shaped. So I found these images awesome. The images that were used to display the observations, like the composite image of the eclipse, to really show not just the fact that the shadow was circular, but the size was the rough size of the Earth's shadow. I thought those were excellent. Sorry, the second one was the ship. I don't think I've ever seen that good an image of the ship where, basically the ship is sinking down below the horizon, as, due to the curvature of the Earth. So you're only seeing the masts. I thought that was a very good example of that. I looked for, when I would teach this, I would look for images of that, and I never found the one that good. So that was really cool. Some questions I had about this one. So the explanation of the Earth won't always cast a circular shadow, that makes sense, but I do think it might be clearer if you brought more specific examples. So for a disk, when would it cast a circular shadow? Well, it would cast a circular shadow if the sun was right below the disk or right above the disk. That would mean that this lunar eclipse was occurring when the full moon, was at its apex, which would be at midnight. So that should be the only time, if the Earth was a disk, that you observed a circular shaped shadow. Now, if on the other hand, you had a lunar eclipse, say, occur at dusk, well, that should give you a rectangular shaped shadow, because if you're on a disk, then the sun would cast a rectangular shaped shadow. That not being what we saw, we always saw a circular shaped shadow, means that the shape is a sphere. Now, this is brought up. I just do think it could benefit from more examples. The piece of evidence that I had always found very, very useful, because it doesn't rely on waiting for lunar eclipses, is the fact that you have changing constellations as you move north or south. And the star Canopus was one that was commonly used in the Greek world, because in the northern Mediterranean, a lot of times you can just barely see Canopus peeking out on the southern horizon. But if you cross the Mediterranean Sea, you go down to North Africa, you can see a lot more of Canopus. And this happens with all sorts of constellations. You move north or south, the stars not only change their apparent angle, they also change what constellations are visible. So I think that this would and this would only be possible if the surface of the Earth was curved. So I think this is a major piece of evidence that I do really think belongs in this in this analysis. Now, another thing that I've always found interesting about this question is the investigation of the objections. And basically how down had to be reconceptualized. So the idea was, well, if the Earth is a sphere, why don't all the people that are not, on the very top of the sphere, why don't they just fall off? Like if down, if you pour water onto a ball, the water's just going to drip off the ball. It's not going to stick to the ball. I think Aristotle had a very interesting reconception of what down meant. He meant that down was towards the center of the spherical object. So down would always be towards the center. It would not be some absolute down that was below the spherical object. Which I think is a very excellent distinction. Aristotle was a master of drawing distinctions. And it's a very excellent distinction to make that needs to be made if you're going to if you're going to run with this conclusion. So there we go. Next, we're going to get into the ideas that involve using geometric analysis, and I think these are just great. So these are some of my favorite. So the first one is the size of the Earth, and the motivation. Basically, it starts with the context of Eratosthenes, and he was intrigued by these stories of the city in Syene, where there was a time of day where, at least there's during some seasons, where there was no visible shadow, meaning the sun got directly overhead. Now, this raised the question in him, well, if the shadows are different there than here, that must mean like the light striking at a different angle, and the reason for this, given he knew at this point the world was round, is that the Earth is curved. So could this difference in angle, could we use some geometry and some measurements of shadows to determine this angle and use that to determine the size of the Earth? And ultimately, he could. So won't reproduce it, but the basic idea is that you do a geometric analysis of the shadows in these two different cities, and you can ultimately, once you do that, you can relate the distance to the two cities to an arc on the circle that forms the circumference of the Earth along that meridian. So it's very important that these things be as close to on the same north-south line as they can be. If it's east or west, then that kind of messes things up. But if they're on the north-south line, then you can relate it to the arc of the circle that can get you the circumference, which can get you the radius of the Earth. And ultimately, they did that and found that the radius of the Earth is approximately 6,371 kilometers. So I really do like these geometric arguments, and I think it's always fun to bring up the meaning of the term geometry, Earth measurement, and really say, well, this was a major tool that people used to figure out things about the Earth. It was not this sort of abstract science that's thought of today. There's lots of boring proofs, but it was a tool people used to make arguments about, things the size that they couldn't even conceive of. So questions I had about this. This investigation, I think, shows one of the classic difficulties in the history of the progression of science, and that is the problem of unit conversion. So Eratosthenes obviously did not use kilometers. Kilometer as a unit was not invented. I believe he used stadia, but I would not swear to that. And it turns out that these conversions, if they were done inaccurately, and the problem was stadia was not necessarily a standardized unit. So you might have one conversion for stadia that was correct, one that was incorrect. But if the conversion wasn't done accurately, this would be a big problem about the progression of the knowledge. So I think not only does this introduce a really interesting method for determining the size of the Earth, but the importance of having standard measurements that you're going to make. Now, another thing, I always thought Posidonius' method was very brilliant as well. And in point in fact, I actually think I like it a little bit more. Maybe a little bit more is a bit of a stretch, but basically his method uses difference in location of the stars. So it uses the star Canopus that I mentioned earlier. Basically to do essentially the same thing. Use the difference in angle to determine the distance between two cities as the arc of a radius. And his method is completely accurate. His numbers ended up being wrong, or at least as far as we know they were incorrect, moving out of antiquity, again due to the problem of unit conversion. Now, Professor Elias brings up Columbus's measurements. I believe that it was Posidonius's measurements of the circumference of the Earth, the radius of the Earth, that propagated through Ptolemy that ultimately got to Columbus. So using this method and showing that there are multiple ways to attack these kinds of problems, I think could be really useful. All right. So next one, the relative distance of the sun and the moon. Sorry, that's going behind the picture there. So yeah. Oh well. So the motivation, it's also going behind the picture. The motivation is that knowing the size of the motivation in question, knowing the size of the heavens might be useful. Can we use these geometric relationships to determine the distance between the sun and the moon? And the idea here is that during a quarter moon, the angle between the sun and the moon is 90 degrees. So the Earth, the sun, and the moon form a right triangle. We can use trigonometry to find the ratio of the moon-Earth distance to the moon-sun distance, or to the the Earth-sun distance, as it turns out. So the ultimate conclusion is that the sum should be the sun is 422 times further away than the moon. So the memorable aspects of then again just using these simple geometric arguments and measurements to do the elegance of the solution is very, very cool. Now, I do have a good number of questions about this one. So I'm going to dig into the motivation a bit more on this one. I could have done that on a lot of these. Is this a valid motivation according to the premises of the course? Knowing the size of the heavens might be useful. So is that valid? I mean, I'm not taking a position on that one way. I certainly think it is a valid motivation, but is just this statement that it might be useful enough to say, well, this research is not a waste of time, or this inquiry is not a waste of time. So I mean, I think that's something you really do need to nail down a bit and think hard about that. If you're going to take this claim of saying certain lines of inquiry are a waste of time because they can't improve the human condition, it's not obvious to me that Aristarchus's inquiry into the relative distance of the sun and the moon had an obvious improvement to the human condition. And if it didn't, if the improvement wasn't obvious, was he justified in doing it? Now, this one also, the nuances of the historical narrative are starting to they're starting to and Professor Elias even notes this, there is starting to be nuance with them. And the main reason here is because a lot of though this method can in principle be done correctly, the numbers that people determined are not exactly right. Now, that is a very interesting thing it's a very interesting thing to note. And why weren't these? Why was this? Why even if Aristarchus's method was right, why were his numbers off? And they were off by a lot. Like, I think his value was like 20 times, not 422 times. So he was off by more than an order of magnitude. So the question then is why? And you can show why this is the case in that just a 1 degree error in measurement is going to triple the ratio. I'm pulling those, but it's going to include huge errors in the ratio of the two sides of those similar triangles. So this is a prime time to introduce the importance of detailed measurement and how limitations in the measurement detail you can make do limit the progression of accurate discoveries. Now, in terms of the approach of the course, this is where we start to get a mixing of the historical narrative with modern numbers. So a lot of times, the things will be presented as Aristarchus doing them, but then with numbers he didn't have. Okay, now that becomes very confusing for me, particularly in the next two ideas that we look at. So again, I have to say, okay, if the value is in the historical narrative, then, it's worth sticking to the historical narrative, and it's worth, sticking to what they could and couldn't measure. And frankly, they could not measure. They didn't have the right measurement equipment, accurate enough measurement equipment to know that this was the case. And I'll show why I think that's relevant in the next couple of slides. I think the next one, actually. Yeah, size of the moon. So the basic summary goes here. And the idea is, can we use a similar sort of geometric analysis to not just determine the ratio of the distances between from the Earth to the moon and the Earth to the sun, but can we figure out the sizes as well? And the idea is that we use the transit of the lunar eclipse to say that the radius of the Earth's shadow is roughly 3 times the radius of the moon. Given that the sun and the moon have the same apparent size, the ratio of their sizes is going to be the same as the ratio of their distances, which is presented as 422. Sun would be 422 times larger, the radius of the sun 422 times larger than the radius of the moon. And then the geometric analysis shows that the radius of the Earth is 4 times the radius of the moon. From that, we can use the known value of the Earth's radius to determine the sun and the moon radii. So again, really like the geometric analysis. This is probably the most advanced one that is done in this presentation, but it's always very interesting, always very fun to look through and to see. And I also thought that the different points on the triangle were well explained as well. That was awesome. So some questions. Again, modern values in the historical narrative. Now, the main this probably qualifies as a critique. But the main problem I have, or the main question I have arising with it, is the analysis done in the lecture required the use of this value of 422, the sun being 422 times larger than the moon. That wasn't available to the ancients. However, I do believe that they were able to get to the Earth is roughly 4 times the radius of the moon. I'm fairly certain Hipparchus was able to do that using a fairly similar method to this. Now, he clearly didn't use the same analysis that is used here because he didn't have that 422 number, so he had to use something different. So the problem here is that it's presented that, Aristarchus did this. Aristarchus or Hipparchus. They did X. But that wasn't what they did, because they didn't have that number. So they did something else if they got to this value. Okay? And again, that's kind of what I was saying there, is that the radius of the moon values were better than the radius of the sun values historically. So why is that the case? It doesn't seem like that is quite accurately presented here. All right. Distance to the moon and the sun. This was the final investigation. Basically, the idea is that can we not just get the size and the ratios of the size of each body and the ratios of the body? Can we actually find the distances, in an actual measurement? So the basic investigation is that if you were to, you could fit around 720 moons or suns to form a complete circle, because they take up around the same, they subtend about the same angle. And then given that you know the radius of the sun or the moon, that would give you the circumference of that circle that is made. And then the circumference of that circle, of that big circle made of 720 moons or suns, you could get the radius of each of those circles, which would then give you the distances to the sun and the moon. And basically, the conclusion is we come up with numeric values for each of these distances. Again, I do like this geometric trick. It's a bit simpler than the previous investigation, but I like the way that it's logical, it's straightforward, it can be easily illustrated. It's a good sort of example of geometric reasoning, and And I think that's very good to present. So at this point, I'm starting to not, and this is even me knowing a bit about the historical narrative, about what happened historically. I'm starting to lose what's actually known historically and what's historical perspective mixed in with modern values. So it's starting to be very difficult for me to distinguish between the two. And that's not necessarily a bad thing, but given how much this relies on sort of the historical narrative, in that, you know, it's presented as Aristarchus was doing these things. Well, Aristarchus wasn't doing these things because he didn't have a lot of these numbers. He was coming up with a lot of these methods, but he was not coming to these specific conclusions. So, it's not. I just think that, particularly if someone's trying to keep that straight, this is actually starting to become confusing by the end here. So that is all I have to say on the investigations. Looking over a bit more of the unit, the reading, assignments, and quizzes, it wasn't clear to me if the practice was supposed to be based on the lecture content or the supplemental readings, or both. I do think that if you want to base it on the supplemental readings, I think that could be tightened up a little bit more. And particularly, you could say, okay, we didn't cover certain things in our lectures, like, say, solar eclipses, and then have those type of questions be sort of grouped together so that the student knows, okay, now the idea is that I need to go read about a different investigation and sort of apply the same method to it. And along those lines, I think that if that's what you want to do, then questions could be more directly tailored to the class. So, for instance, if you want the Mqic method, ask them to put this, the observations of the discovery of the principles of the solar eclipse into the Mqic method. I think that would be a great exercise, and it would further reiterate what you're trying to get people to be able to do with this method. Then I had a question about the purpose of the practice questions. It seems to me that the purpose is to reproduce the reasoning either directly in the same context or possibly in a different context. So, we might move it to Mars. We might move the situation to Mars, where we're going to look at the shadows of the lunar eclipses of the Martian moons and see what we can determine about the Martian moons from that. That's reproducing the reasoning in a different context. I would wonder if it's possible to have the students go through some of the initial inductive reasoning as a portion of the practice. So rather than, the example in the seasons, rather than, saying, okay, these were the things that were observed and then these were the conclusions that were drawn, could you give them the observations and say, okay, what's the correlation between the angle of the sun, between the duration of daylight, and between the temperature? So actually have them do some of the legwork involved in the induction as part of the practice. That's more of a teaching question, like what would be the optimal teaching method, but it is something that came up there. Could you extend the inductive reasoning to a different phenomenon in the practice? So again, this would start to kind of diverge from the historical narrative, but when you talk about the phases of the moon, could you then show images of the phases of the planets, particularly Venus? I think Venus is a very great example of the phases of the planets. But could you show that and, ask students, okay, what conclusions can you come to from the fact that you see these different phases at these different times? Things like that. And then lastly, is the reflection writing at the end, is that for the student or the instructor? So is it is it designed to get the student to be more introspective about what they're going to do going forward, or how they think about science, or is it designed for the instructor to understand what the students struggled with? Because I think either purpose, whatever the purpose happens to be, I think it could be tightened up and the questions could be a little bit better in order to direct it towards that purpose. So that is all I have for this for what I wanted to summarize in this for this lecture. Future summaries will probably be a lot shorter. I won't be going over the general approach again like I did today. But it's a very interesting course to take. And if James wants to discuss, I'd be happy to chat with him about it anytime, anything like that. Thank you for watching.